We're going to review the reproduction of Sutton's work. Let's start out with the random walk experiment setup. We generate all of the training sequences in the same way he does. We're doing error measurement the exact same way, root mean standard error, with actual probabilities of right side termination. The weight update equation is from Sutton's equation 4, which states that the delta of the weights at each step is the change from the current state to the last state, weighted by the learning rate, and then exponentially weighted by the recency of seeing each previous state. So the way this works in code is we actually use the eligibility trace vector, and that allows us to do it incrementally without having to keep all of the gradients. So we increase by 1 the value in the eligibility vector at the state that we previously saw, and then we do the weight update, the delta weight equation. So here again is the weighted value, and then based on the recency of seeing each state. And then we take that eligibility trace vector and decay it by lambda. And this is essentially the same thing as doing the summation of the gradients. Batch TD, we accumulate all the delta weights across all of the training set, and then we update the weight vector. Our stopping criteria, we have to come up with it ourselves, and it's essentially just saying in this experiment that the L2 norm of delta weight falls below a given threshold. Alpha value isn't given to us in this first experiment. Anything sufficiently small, in this case 0.005, is good enough to get the weights to converge, and the result of that matches Sutton's result, monotonically increasing error with larger values of lambda. What this is illustrating is that the testing error is lower as we move from lower levels of lambda. Essentially, you're showing that doing lambda equals 1 is overfitting with the training data, even though that it minimizes the error on the training set. It actually overfits and causes more error on the testing set. Alright, online TD, sequential weight updates. So this is where we update the weight vector after each individual episode. We only go through a training set once. Here we're experimenting to see how lambda values interact. Lambda equals 1 again shows that it has lower predictive qualities than lower values of lambda given any given alpha. And then finally here we're showing that given an optimal alpha for each value of lambda, lambda equals 0 is actually not optimal in this case, mainly because it doesn't propagate values back quickly enough. And so with the limited amount of training data, it takes too long to converge the weight vector. So in this case, it's actually better to have a lambda value somewhere in between 0 and 1. In this case, it's actually 0.3. That's essentially it. All of the data seems to support Sutton's assertions regarding lower lambda values, and the only other thing is that sequential TD has much lower convergence time, so similar error between batch TD and sequential TD, with TD actually having far fewer training iterations. And that's it.